Good afternoon. After we have heard about the exciting new results of the Rosetta mission, I would like to give you a bit of an overview of what we have done in terms of composition of comets over the past 30 years, and compare this a little bit also with what has been achieved in the past 2 years. So, just to remind you, although you know this already, we are interested in comets because they are supposed to be the oldest objects in our solar system. And so we learn a lot about the formation of the solar system from them, and we regard them as the most primitive ones. I used to have here primordial, but I don't put this there anymore because I'm not sure anymore, and this will come up during my talk why I think it may not be as primordial as we think. So comets as such are relics, clearly, of the early solar system, and they are relics because they have been formed at a molecular cloud temperature that is smaller than 30 Kelvin, and were stored for a long time at very low temperature, smaller than 50 Kelvin. The gas phase molecules we know for a long time are similar to interstellar abundance, and we always thought, or think still in part, that comet material might reflect the composition of the pre-solar nebula. Also this I will question later in this talk, and you will then see when. All in all, because of the formation temperature and the storage temperature, we believe that a comet nucleus should contain the most pristine material in the solar system, and large organic molecules, including large organic molecules, and we've just heard about that this is about right with the large organic molecules. And because of this, they should provide the ultimate clues on the formation and evolution of our solar system. At least ultimate in this case means as good as it can be. Here I give a little bit of somehow a preview of what will come at a later stage. What you see here is a spectrum of a circumstellar disk compared with the spectrum of a comet in the infrared. And you see that from the phenomenological point of view, these look very similar. And that was done in the 90s, I come to this at a later point, and actually was the beginning of that people started believing that indeed comets can be looked for in circumstellar disks, and we heard yesterday that this is now actually being done. I couldn't resist this one, although you all know about this. So we have here again a picture of Beta Pictoris, and we see very nice the planet here, and then you see the debris disk here. And so this is the orbit of Saturn, and you can put it on there, then you see that the planet is about at the same orbit. And when I put our solar system on top of it, then you see it neatly fits with the planets, what we have found so far in Beta Pictoris, but this part here is of course completely different to what we have on around our solar system, which is an Oort cloud, which is around the entire solar system. So we have here a picture of the Oort cloud and the Kuiper belt, the two sources of comets and trans-Neptunian objects. The trans-Neptunian objects themselves are regarded to be precursors of at least the short period comets. And now we very, very recently got an object that actually came into the solar system on a hyperbolic orbit. It is called A2017U1. It was found on the 19th of October 2017, so very recently. So we know now that there are objects, in this case it has been designated an asteroid because it didn't show activity, but we know that objects, minor bodies, come from the outside the solar system and enter the solar system. This is the first ever object found. It may be that it takes 20,000 years until the next one comes, but at least this one we've got. So, coming back to comets and the Kuiper belt, you see here an edge-on view on our solar system. This would be the asteroid belt, this would be the Kuiper belt, and then you see a number of comets, Comet Halley and Comet Hale-Bopp, coming in from the Oort cloud, and you see Pluto as part of the Kuiper belt. And the first object that was found in the Kuiper Belt, first trans-Neptunian object, is 1992 QB1. However, actually it's the second object found, because the first object ever found in the Kuiper Belt is this one. It is Pluto. It is in the 3-2 resonance with Neptune, and all the Plutinos have been named, so all the other objects in this resonance have been named after Pluto now. And I show this all because the Kuiper Belt is very important for us. It has objects that are much larger. No, we have detected in it objects that are much larger than the comets we know of. Smaller ones are probably there and we cannot see them because they are too small to be detected. But the Kuiper Belt clearly is also a relic of, a remnant of our solar system. And we have to make sure that we understand also the composition of the objects in the Kuiper Belt. And I think that Pluto and Charon were the first step on going into this direction as well. So, but now we come back to bona fide comets as we know and appreciate them. So, revealing the composition of a comet. Actually, there have been 4 major breakthroughs over the past 30 years in this. And the first one was the Giotto and the Vega missions to Comet Halley in 1986. The second one was 10 years later, 1996 to 1997, which was sub-millimeter observations of Comet Hale-Bopp. Then another one, again 10 years later, Stardust sample return from Comet Will 2, and the last one that we heard a lot about already, again 10 years later, 2015-16, Rosetta Rendezvous with Comet Churyumov-Gerasimenko. So we see progress goes slow, but we have breakthroughs, and there is something like a 10-year lifetime, a 10-year time span between 2 breakthroughs, which is interesting in itself. So we know it is slow, but we continuously go forward with our knowledge. I will now go through all these breakthroughs. Coming closer to recent times, I will go into a bit more detail, and the start I will only summarize what had happened then. So in 1986, we had a number of spacecraft encounters with Comet Halley, and among other things, the gas and dust composition was measured basically with mass spectroscopy, but also for the gas there was a bit of infrared spectrometry involved. What was new at the time is all these parent molecules. Although every comet scientist thought that these parent molecules would be there, they were actually not detected at the time. So they were for the first time detected with the mass spectroscopy on the Giotto mission. What is striking as well is we see only very few, the normal ones, water, CO, CO2, and so on. Only formaldehyde as a distinct molecule of organic nature, and then a number of unsaturated or saturated hydrocarbons where we were not really sure what they are, but we were sure that they were hydrocarbons. In addition to these parent molecules, the so-called daughter molecules, neutrals and ions were found, but these were detected not only by spacecraft, but we knew of them also from ground-based observations already. And actually, it was these molecules from which we concluded that these should be there, and they were then detected by the Giotto mission. With the dust composition, it is slightly different because the dust composition cannot really be extracted by ground-based observations. You have the odd silicon line, but that is about it. From time to time, when a comet falls into the sun, then you might see a sodium or another metal line, but you can't really get the dust composition from ground. And therefore, the mass spectrometry for Comet Halley was extremely important because it came up with all the mineral-forming elements. I'm not going to read them all out because I don't have enough time for this. And on top of the mineral-forming elements that were, of course, expected, there were the so-called Schonn particles, carbon, hydrogen, oxygen, and nitrogen. So small particles that were composed mostly of carbon, hydrogen, oxygen, and nitrogen. And from this, it was concluded that there must be large organic compounds in the comet. So already then, it was concluded that this must be there. However, everybody thought when we thought then of large organic compounds, we thought of molecules of which we could actually get a formula, no matter how big it is, but a formula, and not the material that Hervé presented as the result of what Rosetta found, what the Cosima instrument found on Rosetta. However, in hindsight, we can say that already there we could have guessed that this is so, but of course only in hindsight. What Giotto accomplished was, we could with this confirm that indeed material sublimes off the comet nucleus in form of parent molecules, and they are then through photodissociation and ionization destructed, and the daughter molecules are created, and daughter ions as well, and in the end they are destructed into their elemental composition. Now we come to the next breakthrough, which was not by a space mission. No, it was a lot of luck with this as well. The sub-millimeter technology had just been ready in time to be so sophisticated that we could actually detect organic molecules in sub-millimeter wavelengths. And then Hale-Bopp did us the favor of coming. One of the brightest comets we had, and particularly important because the comet went around the Sun, but we saw it already somewhere very far away. At 10 astronomical units, we were able to detect this comet. So we could follow the comet along its pre-perihelion orbit from 10 astronomical units through perihel and then out again until beyond 10 astronomical units, and could get a full analysis of what the composition of the comet was as a function of heliocentric distance. This was not possible for Giotto or for a mission except for Rosetta that only does a flyby, because that is only one point in time where you have then the composition of the comet at that particular heliocentric distance. While here, this is the production rate of a number of species as a function of heliocentric distance, so this would be perihelion. So here you would see things increasing and decreasing, so you get a feel for what, how the species develop as a function of heliocentric distance or the production rate. And I'm not going into this at all in detail. All I want to tell you is this point and this point are the two most important points on this view graph. They are at 3 AU pre-perihelion and about 3 AU post-perihelion, and this is when the black line and the green line cross. Outside this, the green line, which represents the production of CO, is higher than the black line, which represents the production of OH, which stands for water. And so at 3 astronomical unions, the water production rate gets higher and drives the activity of the comet, while before it was driven by CO. And then when the comet goes back out, it changes exactly the same way around. First, the water is more important, driving the activity, and then it is the CO that continues driving the activity. Compared to what I showed you on Comet Halley, you see that this sub-millimeter technique, combined with this bright comet, was much more successful actually than Giotto. We see the species that Giotto found, but many, many, many more of organic species. And these have all been detected in Comet Hale-Bopp, and in addition there was a number of not detected but upper limits provided, species that were not detected but upper limits were provided. So we see that you don't always need a spacecraft to find something out when the time is ripe for it. In addition, this is not sub-millimeter, but actually infrared. This is the image I showed at the very beginning. We were lucky that the ISO satellite was in space and could take infrared measurements, and Hale-Bopp was there at the right time, so it was there while ISO was operational. And this is when the spectrum of the circumstellar disk, this one here, and the comet were actually obtained, and when it became clearer and clearer that comets should be somewhere in circumstellar disk, and that this is all connected with star and planetary formation. Now I come to the third breakthrough, which is the Stardust mission, the sample return from the Stardust mission. So Stardust went to Comet Belt 2, this is the comet here, and it collected about more than 10,000 particles of the size 1 to 300 micrometers, either on aluminium foil or in a silica aerogel. And here you see what it was collected. This is the aerogel, and here you see one of these little entities here. And everywhere where you see something like this, a particle has impacted. They impacted with a huge velocity of 6 kilometers per second. So they went down, they went in here. These are all the tracks of individual particles. So they went down the tracks and were destroyed in the silica gale. So everywhere some debris was distributed along the track. And then most of the time, there was a terminal particle that could be analyzed. But of course, you could also analyze the tracks. It took them about 10 years to analyze everything, and they are still doing it. However, we know a lot now about this already, and there's an excellent review by Brownie, who was the PI of this mission, that was published in 2014. I can give you only a glimpse in what they did, because it is simply too much to review this now all. So they found mostly rocky materials in these tracks. And they were composed of silicate minerals, amorphous silicates, sulfides, metal, oxides, nitrides, carbides, and organics. I'll give you now two highlights, and then on the next view graph I'll show you more about the organics. So, for instance, they found iron and copper sulfides. And that means these sulfides, this means that there had to be liquid water, because these sulfides can only form if there was at a certain point in time liquid water. That means the comet, there must have been something warm on this comet. Otherwise, this could not have been formed. The other thing is that also, again, glycine was found, which is an important building block for life. And actually, it was first discovered in 1970 in meteorites. Then it was found now in two comets. It's found in Comet Belt 2, and it's found in Churyumov-Gerasimenko. Here the glycine is found in the traces, which you don't see now anymore. So in the more refractory material, while in Churyumov-Gerasimenko the glycine was found in the more gaseous material, more volatile material. But let's come back to the organic matter as such. So these deceleration tracks all show organic matter, or most of them show organic matter. However, they do not show large molecules. No large components are found. The morphological categories are consistent with carbon-rich meteorites and IDPs. But the carbon abundance is lower than that of IDPs. And then, of course, you would think maybe it was degraded due to the capture process. So this is why there is less carbon there, because it's rather volatile. And it appears that this can be confirmed indeed, because the Stardust mission also, on top of the sample return, had a mass spectrometer on board, the SIDA instrument, which you see here, which in situ measured a number of dust spectra. So 29 dust particles were actually analyzed. And indeed, these 29 dust particles coming from Comet Belt 2 show a predominance of organic matter in their spectra. So one thinks everything is fine. It's a predominance in the spectra, so the carbon is degraded because of the tracks and the way they were collected. However, there's more to it. And this is the point that I wanted to make you particularly. There have not only been spectra obtained of the comet, but actually there were also spectra obtained from interstellar grains with the SIDA instruments. And when you compare the mass spectra of the comet with those of the interstellar grains, then you see that the organic material seems to have lost most of its hydrogen and oxygen. So the interstellar grain spectra have much more hydrogen and oxygen in their organic compounds than the comet spectra have. And it may be that these were lost as H2 and CO, which is now present in the comet gas phase. So something was going on there. And In addition, the comet has dust-rich and nitrogen-containing species. Has nitrogen-containing species. So there were no traces of amino acids. However, that doesn't mean that there were none. It may simply be that in the 29 particles that were analyzed, there was none. And also sulfur ions were detected in one of the spectra, and sulfur species are also important in cometary organics. Coming back to the samples, to the tracks and the samples, there were two types of organic material that was apparently unaltered in the sample return. And one was polyaromatic carbonyl-containing matter, and that is similar to the insoluble organic matter that we have heard about earlier by Hervé, and which we know from primitive meteorites and IDPs. So also there, it seems that we see this in two comets, not just in one. And the other one is highly refractory organic material, and that is similar to that in nanoglobules in primitive meteorites and also IDPs. And usually this has a high N15 enrichment. So there is an enrichment in the isotope N15. And that is interesting. I now have to come to something which is between these 10-year steps. This is interesting because it was found in the gas phase as well. In 2002, when the VLT-UVs started to work we could obtain high-resolution spectra of CN in comets, a trace species that is regularly observed, we could determine the isotopic ratio of not only of the carbon, but also of the, but also of the nitrogen. What you see here is just a high-resolution spectra, so of CN. So this is the CN band, and the little peak here, the red one, would be the C13 N14, and the blue would be the C12 N15 band. And from this you can get the isotopic ratios of both carbon and nitrogen, and this is the result. It was measured for many comets at different heliocentric distances, Oort cloud and Jupiter family comets, and it's always the same value. The C2 to the C12 to C13 is always around 91, so it's the telluric value, what everybody expected. And the N14 to N15 is 141, which is only about half the telluric value, which is the telluric value is 272. That means we have a strong enrichment in nitrogen-15. So there is also something there is a relation somehow between the dust and the gas, and we have not yet found it out. So we have to look into this direction as well. I'm almost ready. And very briefly, that was the fourth breakthrough, the Rosetta mission, and I'm not going to tell you much about it because we heard all about it, except for a result from one instrument which I would only want to add for completion. On top of the orbiter instruments, there were mass spectrometers on the lander, and one of them was the COSAC instrument. It was supposed to analyze samples that we would have taken from the surface through drilling and would have then had really material drilled off and not leaving the surface. But it didn't happen, unfortunately, so it worked in something which was called sniffing mode and detected, in spite of this, a number of organic molecules, of which 3 had not been detected before, these 3 marked here. And what is also interesting is that everything it detected, the COSAC instrument, can be easily built from these 4 components: water, carbon monoxide, methane, and ammoniac. And with this, I will stop. And here you see again a picture of Churyumov-Gerasimenko, an interesting comet. And since we are here in the mountains, I thought I'd show you what you could do with this slope as well. And this is now the end.
Thank you very much.